videos. So we're going to start with climate change. So after the ozone slides, which you should have just finished or finished recently, you should be able to do homework 5. So now this is the last set of material that's going to be on exam 2. This is on about climate change. This is homework 6 material. So there's some new stuff here, but it's a relatively short. So this should just be one video. Again, good idea to open up the slides, play the slides along the video. You can pause the video as necessary, go back and forth. So this is a lot of information here. So the greenhouse effect is the idea that's kind of the same as a greenhouse, or something you're probably more familiar with. I'm sure many of you left your car parked outside on a warm day, and you come back and it's oppressively hot inside the car. So it's the same idea. Some solar radiation passes through. In this case, it's the Earth's atmosphere. In the case of your car, it goes through the window, right? Light comes through the window. That's an example. Okay, and then some of it's reflected back, but some of it bounces back in and causes things to happen. So in the case of this, in the case of climate change, so it's usually infrared that causes this. So this is basically what I said. Some heat is radiated back to the atmosphere. You have to have molecules in the air. So if it was in a vacuum, if there was no air, say inside your car, it wouldn't heat up. Okay, so you have to have molecules in the air, and water and carbon dioxide happen to absorb energy in the infrared. The rest of it is of that energy. So then what happens is the energy is used by, it causes chemical bonds to bend and stretch, and then when they release that energy, some of it comes off as heat. So what you can do right now, just to demonstrate it, hit pause, okay, then jump up and down. Okay. Now, after you jump up and down, you'll notice you use energy to push your body up. That same energy was released, but some of that energy caused you to get warm. It's basically the same idea, all right? So heat's transferred by molecules bumping into each other. Of course, closer to the Earth, there's more molecules. Okay. So if you increase the amounts of carbon dioxide and water, let's back up. Carbon and dioxide and water are what absorb the infrared. So if we increase the amounts of carbon dioxide and water in the atmosphere, would you expect an increase in the greenhouse effect or a decrease in the greenhouse effect? You're right, increase. By the way, the greenhouse effect, backing up 2 slides, greenhouse effect is not necessarily a bad thing. In fact, without it, we wouldn't exist, because without it, there would be no heat on the planet. So the greenhouse effect is what keeps us warm. You know, the Earth has to be between a certain set of temperatures for life to exist as we know it. So without the greenhouse effect, we wouldn't be here. The problem is when it starts getting too much, it gets too hot. All right. So this is the famous hockey stick graph that's in Al Gore's book. So you can see that this blue line is global temperature. So you can see it's zigzaggy, kind of noisy, but you can see overall it's trending up. And especially right around here, it really starts trending up. Now in the 1800s, we started having industrialization. It just took a while for there to be an accumulation. And of course, as populations exploded, we got more and more people, more and more things that make CO2 and water vapor. It increases a lot, but you can see that the temperature line and the carbon dioxide line are almost right on top of each other. So now how do we know what happened? So there's temperature data back here, but how would we know what happened, say, thousands of years ago? All right, and that's the way we can tell. I've talked about this in class before. Ice traps gases, and in places like Greenland and Antarctica, there is ice. If you dig deep enough in the ice, some of that ice was put down thousands of years. And so you can literally pull the ice up, capture the gases that are trapped in the ice, because as ice freezes, those gases will just get caught in there like little bubbles. And you can look at what the molecules are, so how much carbon dioxide is trapped there, what the percentage of carbon dioxide is, percentages of methane. Water would be hard to tell because it's ice. And so you can get the amounts of the gases. To get temperatures, a good way to get temperature is you can look at the ratio specifically of oxygen 18 to oxygen 16. So at higher temperatures, heavier things tend to increase in the atmosphere. At lower temperatures, heavier things tend to sink. So from the ratio of oxygen 16 to oxygen 18, you can kind of estimate there's a correlation between that and temperature, because thermometers weren't around 2,000 years ago. But there's good data on this. Whoops. Next slide. This just shows that these things do absorb. This is kind of like wavelength. It's related to it. You can see this is a vibration of the carbon oxygen double bond. So you can see why we looked at structure. So now you guys know what that means. Okay, this is it bending. And these are absorbances of infrared. You may or may not be familiar with the carbon cycle. So the carbon cycle is basically photosynthesis. Plants absorb carbon dioxide to make plant matter. Things that eat plants and other things break down plant matter, which is basically glucose, into carbon dioxide, so it goes back up. It gets absorbed by water, right? It gets released by water. So it's kind of moving around in the air. It moves around. There tends to be, in the absence of increasing, of throwing more stuff, there tends to be, in biology they call it a homeostasis. It tends to be about the same amount until we anthropogenically start throwing things in. So sources of greenhouse gases. We spend a lot of time talking about combustion of hydrocarbons. So hopefully you have memorized the formula. Anytime you burn a hydrocarbon, you're going to form carbon dioxide and water vapor. And what do we burn hydrocarbons for? Pause. Think. Exactly. We use that as a source of heat, as a source of energy. We'll even talk about that more later. Methane also is a big greenhouse gas. It actually absorbs more than CO2. It's just not quite as abundant. Methane is formed by fermentation by bacteria. So fermentation is metabolism in the absence of oxygen. So when there's no oxygen present, organisms, especially bacteria, can still derive energy, but they make methane. Also, cow farts. So a lot of big feedlots and things like that. But it's not nearly as abundant as carbon dioxide. Nitrous oxide from catalytic converters, also from bacteria. Ozone, okay. Sulfur dioxide, again, not terribly high. So the big thing is really carbon dioxide, but these are also contributors. I want to make sure you realize that climate change, global warming, and ozone depletion are not the same thing. They're related in that they're both environmental things, but they're completely different in terms of the processes. All right, and we'll talk about that just to remind you. Now, how do we know what's going to happen? So climate is a very, very complex thing because you've got large areas. By the way, there is a big difference between climate and weather. So weather is local and over a couple of days. Climate is global and over long periods of time. So weather could be for a year, climate could be for a decade. But this type of stuff is based on a lot of data and extrapolation, because we look at data and we say, well, what's going to happen in 10 years if we keep this? It's a big computer model. And in fact, the data had been gathered for a long time, but until really the early 90s, when computer power got much better. And just to put it in perspective, think about the phone you have now and say the first phone you may have gotten, or even an early generation computer when you were a kid if you had a computer in your house, or even your TV, and look at how much technology has changed and how much information can be sent even in the last several years. So to handle all the data that was gathered, the computer power wasn't there, but now it is. And so we just do computer modeling and we say, well, if this increases by this much, what will that do to this and this? Data actually comes from measuring temperatures all over the world, measuring airspeed, wind speed, absorbance of light at various wavelengths. I did a couple of summers setting up a system that would gather things like that, including aerosols and pollutants, all sorts of stuff, temperature, humidity. Okay. Oops, keeps doing that. So other variables, the oceans are a big carbon sink. However, gases are less soluble in warm liquids in general. So you can try this at home if you want, but from experience, if you put water on to boil, right away you see bubbles. Okay, the first bubbles you see when water boils are not actually boiling. It's gases that are dissolved in water, like oxygen and carbon dioxide. So if you heat things up, so if the oceans get warmer, gases that are trapped in the water, like oxygen, carbon dioxide, will come out into the atmosphere. And so what that does is it becomes, 1 + 1 = 300, right? Ocean circulation can decrease. Circulation of the carbon dioxide would decrease because less of it would be absorbed. Aerosols, we talked about this, okay? But aerosols do is they scatter light. So a good example of light scattering is if you look at anytime a beam of light comes through your window, if there's dust in the air, you can literally see the beam of light, or driving your car at night when it's foggy, you can see the light hitting water particles in the air, where if there's nothing in the air, the light just goes through and hits the ground. So that's what light scattering is. Light scattering prevents the energy from being absorbed, and so it tends to lower aerosols. We can have aerosols can be nuclei for clouds. Water vapor needs a surface to form liquids on, and clouds can reduce global warming as well. Okay. Albedo is the reflectivity of a surface. So the more energy is reflected back, the less that stays on the planet. So that's why there's been a movement to make more concrete roads rather than asphalt roads. New roofs tend to be lighter colors to reflect more light back. And of course, population growth. And population growth is a big deal because what do people do? Well, we metabolize, so we exhale, but we also use energy. All right? So the big question that some people don't believe, is human activity significant? And the answer is absolutely. Most of the changes have happened in the last century. 2017 was the third hottest year on record. Industrialization is a result of human activity. Excuse me for banging my leg. Okay, so I'm sorry, I clicked a slide. So what's going to happen? Should I buy a beachfront property in Arizona? Well, what happens too is as ice melts, the sea level will rise. So you realize that Antarctica is not a big ice cube. It's a land mass. The ice is not in the water. So when the ice melts, it'll go into the water. All right, so sea levels will rise. So if you're living, Del Mar, things like that, low-lying areas, there are entire countries whose net elevation is 2 inches. You'd expect more rainfall. What likes water? Bugs, diseases, things like that. I can't say that this coronavirus has anything to do with climate change. I haven't heard anybody say that. But who knows, right? But certainly bugs, and of course bugs carry diseases, things like malaria. So what you would expect is the tropics would expand. Malaria is an example. It's carried by a mosquito. Okay, you'd expect more intense storms. We're already seeing that. Increased summer droughts. So you'd expect more extremes in weather. So some solutions to climate change. And of course, this is a big issue in the current political campaigns, right? The Democrats have a Green New Deal where it has some pretty drastic measures to really, really combat carbon dioxide being emitted into the atmosphere. There was a Kyoto Protocol in the 90s, the Paris Accord, which a lot of countries signed. Our country backed out of it. It was non-binding though, so it was just so to speak an agreement. There was no penalties that people didn't abide by it, but it's very symbolic to not be a part of that because this is not just one country, this is world. Okay, certainly things you can do, switching to energy sources like solar, walking, not driving as much, just adjusting your thermostat so your heater doesn't come on quite as frequently. And I've talked about this a lot in this class. You don't have to do big things to make an impact. If everybody does a little bit, it makes a difference. You're not a factory. You're not producing huge amounts of carbon dioxide and water vapor, right? The regulations don't really apply to individual citizens, but certainly, you can combine trips. You walk across the street to 7-Eleven instead of driving. Things like that, little things you can do. I said something as simple as setting your thermostat so in your home so it comes up and doesn't get quite as warm when you use your heater. 1 degree might make a big difference. Not only that, it saves you money. So most of the things that people are being asked to do save a lot of money on an individual basis. All right, so that's the end of this set of slides. So at this point, you should be able to do homework 6. Exam 2 goes up to here. And yeah, you can look at the schedule when that's going to be.